Hello, so we've spent a little bit of time kind of warming ourselves up, getting ourselves familiar with this kind of idea of series, okay? But now I'm actually going to show how series can be used, or power series can be used when it comes to ODEs. Okay, so remember that we've looked at how to solve a second order differential equation of this kind of form. So second derivative plus some constant times the first derivative plus some constant times y equals something on the right hand side. Okay, so let's just say q of x, say. So yeah, that's fine. So basically, we've looked at how to solve these things where these coefficients here were constants. All right, but now what we're going to look at is the case where the coefficients are variable. In other words, they're some function. So for example, our independent variable in this case is x, because we're looking for a solution. A solution, remember, is the function that fits this thing. So we plug the first derivative, and the second derivative in here. But the variable that the function is of, if you like, so the function is of, is called the independent variable. So in this case, our independent variable is x. Okay, so in other words, we're looking for y is equal to something like, I don't know, x squared plus 3x plus 4. Yeah, that would basically say, well, this basically says that the independent variable is x, because it's the thing which y is dependent on. Y is a function of x. Okay, so that's all independent variable basically means. So basically the idea is now that we're looking for variable coefficients, so in other words a and b, that are functions in themselves. Okay, so first of all, what we're going to look at is going to look at the general form. I'm only going to consider the homogeneous form, because as you've seen with kind of first order differential equations and second order differential equations, if you can get the homogeneous case into your head, then the non-homogeneous case just kind of follows on exactly the same way. Okay, so here's the general form that we're going to be looking at. Okay, so we're going to be looking at some function which I'm going to call p of x. Okay, times by the first derivative, so let's say dy by dx squared. Sorry, second derivative, which is d2y by dx squared. Okay, plus some function, let's call it q of x, times the first derivative, so dy by dx, plus another function, let's call it r of x, times just by our function y. Okay, and again, I'm just going to consider the homogeneous case. So in other words, this right hand side is going to be equal to 0. Okay. What we're going to do first of all, I'm just going to introduce this, just kind of make this point now. It's not a big point, but basically we're going to assume that P, Q, and R are all polynomials, okay? Because that makes them continuous. If they're polynomials, then they're continuous. Every polynomial is continuous. Basically, continuous is where you can draw the function without taking your pen off the paper. Okay, so there's no discontinuities, there's no jumps like this, for example, or anything like that. So yeah, we're just going to assume that P, Q, and R are polynomials. However, the same works if they're analytic functions. So for example, e to the power of x, or cos x, or sin x, or something like that. Because of course you can approximate these using the Taylor series, which effectively has the same form as a polynomial. Okay, it's just going to be an infinite polynomial rather than a finite polynomial. So a finite polynomial is basically like x cubed is a polynomial of order 3. Yeah, so it's like this thing expanded up to the power of 3. Yeah, so hopefully you can see that, if we just consider these as the PQR as polynomials, then the same is also going to be true for this, for kind of other functions as well. But yeah, just for simplicity, we're just going to consider P, Q, and R as polynomials. All right. Now I'm going to introduce a new term that is kind of quite important. It makes sense, but it's quite important. And the term is an ordinary point. An ordinary point. Okay. So basically, we have the same things we had before. So I'll just write this down to remind us. So we've got this thing up here. I've just denoted the second derivative by y dash and the first derivative by y double dash and the first derivative by y dash, just for simplicity. Okay, so this is just what we had. Okay, we're going to assume, now what we're going to do is basically we're going to assume that this p, q, and r, so p of x, q of x, and this r of x, okay, they're variable coefficients, but they're polynomials. Okay, but more crucially, they're polynomials with no common factors between them, okay, and that will become important in just a moment, and hopefully you'll see why. So basically, what I mean by no common factors, if I divide one by the other, then I can't break it down further. For example, if I have 3 and, let's say 3 and 10, then 3 shares no common factors with 10, okay, maybe actually that's 3 and 10, fairly obviously because 3 is prime, but yeah, 3 and 10 share no common factors. Whereas if I write down something like 3 and 12, then, they both share a common factor of 4, which means that I can break this down into a quarter, yeah? So basically what I'm saying is if they've got no common factors, when I divide them one by the other, then they're not going to break down any further, okay? And again, we're going to consider this second order differential equation close to some point. So close to some point, so we're going to consider it close to some point x naught. In actual fact, when we consider something very, very close to that point, so in other words, if we've got, if I just plot it out on a number line, okay, we've got this point x naught, and I'm going to consider like this points which are very, very close to it. So say, for example, I'm going to consider x naught is 3, okay, then I might consider, say, 2.99, okay, and say 3.01. Yeah, so I'm considering values that are very, very close to 3. Okay, and that's something called a neighbourhood, and that kind of makes sense, right? Where you live, okay, in the relative to the world, okay, you've got your own little house in sort of particular part of the world, okay, and then all of the houses which are close to you are what's known as your neighbourhood, right? But you see, say, I live in, say if you live in London, for example. And, you might have a neighbourhood which is sort of within, I don't know, about a few hundred metres of you, yeah? But you wouldn't describe, say, a city in, a house in Glasgow as being part of your neighbourhood. You're only looking at values that are very, very close to your point, okay, to your house. So that's all a neighbourhood basically means. It's just we're just considering a point x naught, which is and points which are very, very close to x naught. Okay, so that's basically the idea here. Okay, and we're now going to remember what we're trying to get here. We're trying to get ordinary point. Well, we basically say that x naught, the point which we're interested in, is an ordinary point if, when we put it into one of these functions, let's say we put it into p of x, okay, so we evaluate our function p, our polynomial p, at x naught, okay, if it doesn't come out as 0 at that point, then it's an ordinary point. Right? And that's important, right? So, and it's not just 0 then, if our function, our p, evaluated at x naught is not 0 at x naught, then it's also not going to be 0 at points which are close to x naught. Yeah? Because we're talking points which are really, really close to x naught, right? And also because it's continuous, there's not going to be any jumps. So in other words, the function is not going to jump to 0. Let me try and draw out what I mean by this. Okay, so let's say we have a function that looks like this, okay, and we've got a function that perhaps looks like this. So it's a cubic function, let's say, it looks like this. This is x, and this is our function. So let's say p of x. Okay, so this is our function p of x drawn on here, okay? And basically what we're going to do is we're going to consider, so this is 0 here, we're going to consider a point x naught, so this point up here, on our function, yeah? And then we're going to consider points which are really, really close to x naught. Now, I know I've blown this up, but basically we're going to consider points which are really, really close to x naught. So because that point doesn't go to 0, then basically what that means is that the points really, really close to it also cannot go to 0, yeah? Because if it did go to 0, if those points did go to 0, so say, you might say, for example, what happens if we consider a point which is, say, down here? Okay, so a point really, really close to 0. We might consider a point which is, in the neighbourhood, which does go to 0. But that's not the point. You've not properly understood what a neighbourhood is then, because a neighbourhood is basically points which are so close to that point that they are basically that point. Yeah? So in other words, if any one of those points goes to 0, then it must mean that x0 makes the function 0. Yeah? So basically, any point which is really, really close to it is basically behaving exactly the same way as x naught. That's the point of a neighbourhood. Yeah? So all the points in that neighbourhood are going to behave in exactly the same way as x naught. In other words, they're going to share a function value that's very, very similar to x naught. Yeah? And so basically, if p of x naught is not equal to 0, then we call that an ordinary point. Okay, so it's just terminology, right? Okay, so this is what we've got. I've basically said that x naught, this is the point that we're looking at. We're considering this second order differential equation around our ordinary point x naught. Okay, and because it's ordinary, that basically means that x naught is not equal to 0. Now, why is that useful? Well, basically, if we divide through by p of x, then basically, because it's not 0, we can do that. Because, of course, if it was 0, then we'd be dividing through by something which is 0. So anything divided by 0 is going to go to infinity. So then, we'd be ending up with a problem. All right. So in other words, if we divide through by p of x, our function p of x, because we're considering the differential equation around x naught, so we can do this. Okay. If we divide through by p of x, look what happens. P of x, okay, and divide through by p of x. So we divide every single term through by p of x. Well, this thing is just going to go to 1. It's p of x over p of x. That's just going to go to 1. So therefore, what we basically turned is this thing here is to become monic. You know, this differential equation has become monic. And oh yeah, by the way, we've got 0 divided by p of x here. So that 0 divided by anything is still going to be 0, right? So basically what we've turned is we've made our lives easier. Oops, there should be a y there. We've made our lives easier just by basically getting rid of this coefficient at the front here. Getting rid of that coefficient at the front here. Okay, so now basically if we say, well, if we let a of x equal q of x over p of x, okay, q of x over p of x, so in other words, that thing we just turn into a of x, right? Just to make our notation look nicer and make our notation look simpler. And if we then, let's say, I don't know, b of x equal this coefficient here, so in other words, r of x over p of x, okay, so in other words, what we end up with is, let me just write this out, we end up with b of x here. Okay, that suddenly looks a whole lot nicer and it looks a whole lot simpler to deal with. Okay, it looks a whole lot simpler to deal with. And we can do that because we're considering the differential equation around x naught, which we said is an ordinary point. So therefore, because it's ordinary, our p function doesn't go to 0. And so therefore, you know, we end up with this. So then we can divide through by p of x to make it easier. Now, let's try and look at these. Now, let's try and look at these coefficients then. Because these coefficients will actually tell us an awful lot. We've said that P, Q and R are continuous. So let's bear this in mind. So P, Q and R, you know, I mean, of course, R of X as well. These are all polynomials, are continuous. Okay, oops, are continuous. So these polynomials here are continuous, right? And more crucially as well, they've got no common factors. They've got no common factors, right? So, okay, let's just talk a little bit actually about why no common factors is important, because we'll start to see why no common factors is important. Because if you look, because these share no common factors, it means it can't be broken down any further. So say, for example, Q and P don't share any factors, which means that we can't break down Q and P. So, for example, you know, if they did share common factors, then there was always the risk that we could turn Q over P into R over P. Yeah, and there's always that risk, or vice versa. So we could always turn, you know, one back into the other. But because they don't share any common factors, we know that A and B are not identical. We know that A and B are not identical, right? And now let's look at the fact that P, Q, and R are continuous. Well, look what we've got here. We've got a continuous function over a continuous function which is not 0. So therefore, what we will end up with, we're going to end up with a continuous function. So therefore, A is a continuous function. Okay, same kind of logic with this. We've got a continuous function over a continuous function which is not 0. Therefore, B is also continuous, right? So, do you remember the existence of uniqueness theorem? Basically, it was a really nice theorem which basically said, providing that these coefficients here are well-behaved functions, that are nice functions, in other words, they're continuous, okay, then given some initial conditions, there must exist a unique solution. So in other words, what this is basically saying is there is a solution to this by the existence and uniqueness theorem. Okay, so let me just write this out. Okay, so this is it written out. Basically, this is what we've got now: a second-order differential equation with variable coefficients a and b, and we've just deduced that a and b must be continuous. So therefore, providing that we're given some initial conditions, there must exist a unique solution. Okay, it's unique because we've got given some initial conditions. So in other words, it hones it in. If you remember, think of a bomber pilot during World War II. Okay, a bomber pilot could be told to go and bomb Germany. Right? Well, Germany's a massive country, so it could literally bomb anywhere in Germany. It's huge. There's loads of possibilities to choose from. And that's, if you like, a general solution, okay? But if he's given some coordinates, then basically the bomber pilot knows exactly which place to bomb. So in other words, the coordinates correspond to the initial conditions. Therefore, suddenly you know exactly which solution you need. Okay. So therefore, then by the existence of uniqueness theorem, because you get given some initial conditions, there must exist a unique solution. The existence part of it corresponds to the fact that A and B are nice functions, well-behaved functions. They're continuous. Okay. And the uniqueness part of it corresponds to the initial conditions, okay? And that's just by the existence and uniqueness theorem. So, okay, we've talked about ordinary points, but there are also another type of other type of point. So, an ordinary point okay, is if p of x naught, if p of x naught is not equal to 0, okay, that's what's known as an ordinary point, okay. Well, there is another type of point called a singular point, okay, which, you've guessed it, is if p of x naught is equal to 0, which is if p of x naught is equal to 0. Now, some of you may come across singular points before. Basically, a singular point is, or if a function is singular, if it goes to 0 at a particular point. Okay, so in other words, if x naught makes a function go to 0, then basically we end up with a singular point. Why? Well, remember what we had. We had that, a of x is equal to, what was it? Was it q of x over p of x? Yep. And b of x is equal to r of x over p of x, okay? Well, now suddenly, if that's 0, then basically what we end up with is we end up with q over 0, okay? Which, of course, goes to infinity at that particular point, at x naught. So I should really replace this by x naught, I suppose. Okay, I should replace this by x naught. X naught, x naught, x naught, x naught. Okay, and likewise for here, we've got r over 0, which, of course, goes to infinity. So in other words, at that particular point, at that point, x naught, because p of x naught goes to 0, then therefore we end up with something like this. So we end up with our coefficients going to 0 at that particular point. Okay, so a singular point is, if you like, a point where the function is not well behaved. It's not really defined. So an example of this would be 1 over x. At the point x equals 0, then that would be known as a singular point, because that makes the function misbehave at that point. Okay, it's a singular point, right? But yeah, eventually, if you understand ordinary point, then singular point is just the opposite. Okay. And fairly obviously, because I've said that P, P, Q, and R share no common factors, then basically we know that because if P goes to 0 at that point, then Q can't go to 0 and R can't go to 0. So if P equals 0, then that implies that Q cannot be equal to 0 and R cannot be equal to 0. Okay. So, yeah, because they don't share factors. That's kind of like a little sideline. But basically, the point which I want you to get out of that is that A, if it's a singular point, then A goes to infinity and B goes to infinity. So, therefore, the function becomes unbounded. So, in other words, it goes to infinity, okay, as the function approaches x naught, all right? So therefore, we can't really apply the existence and uniqueness theorem to talk about solutions at that particular point. So, in other words, if we're considering trying to solve an ODE, second order ODE, where are we? Of this form up here, so the y double dash plus a of x y dash plus b of x y, and if we're trying to consider it around a singular point, so in other words, the point x0, okay, x naught, then because the function goes to infinity at that point, yeah, we can't really talk about a solution at that point. All right, so we're actually going to come back to this later on in the course. But essentially, all I want you to get out is that if it's an ordinary point, it means that we can evaluate a solution to the second order ODE at that point. Okay, if it's a singular point, so in other words, the function, but in other words, we end up with something that goes to infinity, so it becomes unbounded, polynomials become unbounded, then therefore we can't really talk about a solution at that point just yet. We'll come back to this later on. Okay.